Welcome to the g.c.2.4 extension of the radius drawn to tangent concept from 2.4. If you remember, a radius drawn to a tangent or vice versa forms a right angle. And so the first two types of problems we're going to look at are called common tangent problems. You'll see in this first diagram we have two circles that are externally tangent. We're given the radii of both circles, and we'd like to figure out how long the segment is that connects the two circles. And so the procedure is pretty standard, and it's all diagram. First, connect the centers of the two circles, and then draw in the radii to the points of tangency. And mark what you know as you go. So we have that the points of tangency with the radius of each circle forms a right angle. And then here we want to form a right triangle and a rectangle. So we are going to draw in a segment from the smaller circle center parallel to the tangent to form the right triangle on top and the rectangle up top as well. And so now we can insert information that we know. We know that the smaller circle's radius is 8. And then being a rectangle, we know that this part of the rectangle is also 8. We are also given the radius of the big circle is 18. And so I'm just going to put that information wherever I know it, and then look to solve for the missing part of the triangle, the rectangle, so I can get the tangent. And if you notice here, we can insert that this part not drawn to scale is 10 if 8 and the value need to equal 18 for the radius of the big circle. We also can see here that the hypotenuse of this right triangle here, and that's where it's important that you draw on the right angle, is 26. So I don't know if you see, if we can get this part of the triangle, then that'll translate to the opposite side of the rectangle, and I'll have solved for the missing length. And if you look here, this is a 5, 12, 13. So 5 times 2, 12 times 2, and 13 times 2. And so the missing part here becomes 24. And as it's a rectangle, we have that the common external tangent is 24. If you take a look at the next problem, we are given a similar scenario, but this is called a common internal tangent. You'll see that points of tangency are drawn on the circles, and we'd like to figure out how long that segment length is. And so looking at what we are given that the two circles are 2 units apart, so I'm going to draw that in right here. And actually, before I do that, let's go ahead and follow the procedure. Let's draw in the line of centers. Let's draw the radius from each circle to the point of tangency. And then I'm looking for a right triangle and a rectangle. And so from the smaller circle center, just as with the previous problem, draw in a segment that is parallel to the common tangent. And then I'm going to draw in an auxiliary segment so that I can complete the big right triangle. And now I can better insert the information we're given. So the circles are 2 units apart. And so that's going to be right here. And I know that the radius of the small circle is 5 and the radius of the big circle is 10. And from here we're looking to complete the big right triangle so that when we get the missing segment for the big right triangle, then it'll automatically translate with the rectangle that we formed. And so from here, if we have 5 as the radius of circle P, then we have 5 is going to translate to this part of the rectangle. If you look at the big right triangle, we have 15 for one leg. And then here we have, if you kind of translate the radius of circle P right here as well, we have 5, 2, not drawn to scale, and 10 make up the hypotenuse of the big right triangle. And so that becomes 17. And then if you look at the missing measures that you have, what 15, 17 is a triple coming back to you from unit 2, and that would be 8, which then translates to the common internal tangent. And looking at the next two problems, these are versions of walk-around problems where we have unknown measures, and we're going to walk around the figure to figure out those unknown measures. And so if you look at the problem for 3, we are told that the segments are tangent to the circle, and we'd like to figure out the missing side. So we want to figure out this right here. And so what we do with unknowns is we assign it a variable, and I'm going to assign just a part of it x. I'm going to assign this tangent right here to be x. And from a previous concept, we know that two tangents that stem from the same external point are going to be congruent if drawn to the circle. And so if I know that the one part I initially assigned is x, then I know that the other segment extending from that point tangent to the circle will also be x. And then here, if this whole segment is 12, then how would I get this tangent, for example, and I would do 12 minus x. But then this tangent is going to be congruent to that length, which is 12 minus x. And then if this whole segment here is 20, then technically this part that I've just drawn the caret in is going to be 20 minus whatever the 12 minus x is. This is the part that most people mess up just because of arithmetic. Make sure that you distribute the negative to both the 12 and the negative x. And then we get that both of these segments here turn out to be 8 plus x. And then the last piece is if this whole segment is 15, then I need to take 15 minus whatever 8 plus x is to get the missing length, and I'll get 7 minus x. And then I'll get 7 minus x, and I've just walked around the entire figure. Then you might be asking, okay, but we still need to get the measure of the side. Well, the side is going to be both of these parts added together. So 7 minus x plus x is 7, and I'm done. The alternate walk around is going to be the last example on this page where you are given measures between two circles that are externally tangent, and then you have 3 circles are put together and you want to figure out the radius of each circle. There are a couple different ways you could do it. You could walk around, or you can kind of do a variation of the walk around. I'll go ahead and start with the walk around. We're given 12 for AB. We are given BC is 16. And we are given 14 for AC. And so I'm going to assign any radius of any circle to be x, so we'll start with A, and then I'm going to walk around. So if the radius of circle A is x, I have at least these 2 segments, and then if the top segment is 12, AB is 12, then I know 12 minus x is going to be this part of the segment AB, which then is congruent to this radius of circle B. And then if I know that this whole part for BC is 16, then 16 minus, so I'm going to draw this out here, 16 minus whatever 12 minus x is going to get me that missing measure, which is going to be 4 plus x. And if that's the radius of circle B, 4 plus x, then this part here is also going to be 4 plus x. And so similar to the previous example, I'm going to go ahead and take these 2 parts that add up to the whole, and we know that the whole of AC is 14. So x plus 4x equals 14. Oops, I've written that wrong. X plus 4 plus x equals 14. So that's 2x plus 4 equals 14. That's 2x equals 10. And that's x equals 5. And I've figured out the value of the radius of circle C. And so from here, I would look to go ahead and plug back in and get the other radii. And ultimately, you would get the radius of circle C is what we solve for. So that's 5. You get the radius of, oops, and by circle C, I mean circle A. And radius of circle B would be 7, and radius of circle C is going to be 9, and that's a simple plug back in. 12 minus 5 is 7, 4 plus 5 is 9. If you feel comfortable with that approach, I'm also going to then address and erase much of this work. So if I had walked around both sides of the triangle, since I do know several different values, I could have said, okay, if this whole segment AC is 14 and the radius of circle A is x, then this part here is 14 minus x, which is then also going to be this part of circle C, the radius. And then similar to before, this would be 12 minus x, and this would be 12 minus x. And I could have then added 12 minus x and 14 minus x to equal the 16 that I have for segment BC. And you would see that we would get x is still going to equal 5, and that's going to be the radius of circle A.